There is a particular kind of intellectual comfort that human beings carry quietly through their lives, a deeply embedded assumption so familiar and so unexamined that it rarely ever surfaces into conscious thought. It is the assumption of symmetry. We walk to a destination and we walk back. We drive a car across a city and we drive it home. We send a signal across a wire and we receive a reply. The universe, we quietly assume, is a generous two-way street, an even exchange of effort and return, a balanced ledger where going somewhere and coming back require roughly the same cost, the same energy, the same underlying physical logic. That assumption, when applied to interplanetary travel, is not merely incorrect. It is a profound misreading of the geometric and thermodynamic structure of physical reality itself. Consider something simple and immediate. Imagine a pristine glass of perfectly clear water sitting on a heavy wooden table directly in front of you. You hold a small mechanical dropper of dark black ink a few inches above the surface, and you release one single heavy drop. Watch what happens. The ink strikes the water, and it disperses. It spreads outward in slow, beautiful clouds, spiraling and expanding until the entire glass is permanently stained a deep, turbid gray. That process happens effortlessly. It requires no external input of energy. It requires no elaborate engineering. It simply occurs because the foundational mathematics of the universe favors it. The state of maximum disorder, of maximum dispersal, of maximum spread is overwhelmingly more probable than the concentrated state of a single dense drop sitting in isolation. Now reverse the scenario mentally. Imagine demanding that every single one of those billions of dispersed microscopic ink molecules reassemble themselves with absolute geometric precision back into a single dense concentrated drop and launch themselves upward off the water surface back into the glass dropper. The sheer computational and energetic scale of what that reversal demands is almost impossible to fully articulate. You would need to locate every molecule, calculate its precise trajectory, reverse its momentum with complete accuracy, and coordinate the simultaneous movement of an astronomical number of particles against the overwhelming flow of probabilistic physics. The universe does not simply resist this reversal. It resists it with the full mathematical weight of the second law of thermodynamics, with the entire arrow of cosmic time, with every probabilistic bias written into the structure of physical law since the beginning of the observable cosmos. That ink and water is not a metaphor loosely borrowed for dramatic effect. It is the precise mathematical model of what launching biological human beings to Mars and demanding their return actually represents at the level of fundamental physics. The second law of thermodynamics is one of the most inviolable statements in all of physical science. It declares that the total entropy of a closed system, meaning the total measure of disorder and energetic dispersal, will not spontaneously decrease over time. Systems naturally evolve from states of higher concentrated order toward states of lower concentration, higher dispersal, and lower available energy. This is not a tendency or a preference or a statistical leaning. It is a statement about the overwhelming asymmetry of probability embedded at the foundation of the cosmos. Earth is a profoundly energetically concentrated environment. The biosphere, the industrial infrastructure, the chemical processing plants, the mining operations, the fuel synthesis facilities, all of this represents an extraordinary accumulation of low entropy, highly organized energy capable of performing enormous physical work. When an engineering team builds a rocket on Earth, they are drawing from this deep reservoir of concentrated order, compressing chemical potential energy into propellant, organizing matter with extraordinary geometric precision into a vessel capable of fighting planetary gravity. That launch from Earth is itself an enormous expenditure of concentrated energy, but the infrastructure to create that energy exists here. The thermodynamic foundation to support it is present. The return journey home, the climb back out of Earth's gravity well, is already accounted for in the mission architecture before the rocket ever leaves the ground. Mars is not Earth. Mars is a frozen, geologically dead, atmospherically thin, magnetically naked world sitting 400 million kilometers away at its farthest orbital separation. When a spacecraft successfully navigates the interplanetary void and descends through the Martian atmosphere toward the surface, the physical transaction being executed is straightforward at the thermodynamic level. Enormous kinetic energy acquired during the journey is surrendered. The spacecraft falls down a geometric depression in space-time created by Martian mass and is decelerated and captured by it. The energy budget of the inbound journey involves the release of stored chemical propellant working against the gravitational geometry of the solar system, followed by a final gravitational capture. The outbound journey from Mars is an entirely different physical category of event. Albert Einstein's general theory of relativity describes gravity not as a force in the classical Newtonian sense, but as a geometric feature of four-dimensional space-time. A massive body like a planet warps the geometry of the space-time surrounding it, creating a depression, a curved region in the fabric of space and time into which objects naturally fall. The geometry of falling inward along that curved space-time depression is a natural trajectory. It requires no additional energy input because the geometry itself guides objects downward and inward. Arriving at Mars is geometrically natural. It follows the curvature of space-time just as a marble rolling across a curved rubber sheet follows the depression created by a heavy ball placed at its center. Leaving Mars requires climbing back out of that geometric depression. It requires fighting the curvature of space-time with directed, concentrated energy, accelerating mass away from the depression against the continuous resistance of the warped geometry. The Martian escape velocity is approximately 5 kilometers per second. That means any vehicle carrying biological passengers must reach and sustain that velocity using propellant synthesized or stored on the Martian surface. There is no alternative physical pathway. The geometry of space-time does not offer one. And this is where the thermodynamic and geometric problems converge into something that begins to resemble a physical trap rather than merely an engineering challenge. Synthesizing rocket propellant on Mars demands energy. That energy must come from somewhere. The Martian atmosphere is composed primarily of carbon dioxide at a pressure roughly 1% of Earth's atmospheric pressure. While chemical processes can theoretically use carbon dioxide and water ice to produce methane and liquid oxygen through a reaction sequence known as the Sabatier process, each step in that chain requires precise thermal management, pressurized reaction chambers, reliable electrical power, and continuous operational maintenance. The electrical power itself must come from solar panels operating at reduced efficiency due to Mars receiving roughly 40% of the solar irradiance that reaches Earth, or from a nuclear fission source of limited operational duration. Every single component in that propellant synthesis chain must survive the Martian environment. The temperature swings on Mars can span more than 100 degrees across a single day. Dust storms of planetary scale can reduce solar panel efficiency to near zero for weeks or months at a time. Equipment fails. Seals crack under thermal stress. Reactions slow or halt when temperatures drop below threshold values. The asymmetry becomes visible in stark terms. Arriving at Mars is a process the universe fundamentally supports because it follows the natural geometry of space-time curvature and the thermodynamic tendency toward dispersal of concentrated energy. Leaving Mars is a process the universe fundamentally opposes because it requires building up concentrated order, synthesizing stored chemical energy, and then expending it all in a violent directed thrust against the very gravitational geometry that made landing straightforward. But the geometric and thermodynamic barriers are not the complete picture. They are not even the most viscerally immediate danger to biological passengers waiting on the Martian surface. Time itself becomes a weapon. The Earth is wrapped in a magnetic field generated by the convective motion of molten iron in its outer core. This planetary magnetosphere acts as an enormous invisible shield, deflecting the continuous stream of high-energy charged particles emitted by the Sun. The solar wind, composed of protons, electrons, and heavier ions traveling at hundreds of kilometers per second, is continuously intercepted and redirected by the Earth's magnetic field before it can reach the surface and penetrate biological tissue. Mars lost its global magnetic field billions of years ago when its core cooled and solidified sufficiently to cease the internal dynamo mechanism. The Martian surface today is essentially unshielded. High-energy solar particles strike the surface with little attenuation. Galactic cosmic rays, high-energy particles originating from outside the solar system, penetrate the thin Martian atmosphere and reach the regolith. The radiation environment on the Martian surface is roughly 200 times more intense than what human beings are exposed to at the surface of the Earth. Biological tissue does not respond gracefully to prolonged high-energy particle bombardment. Ionizing radiation breaks chemical bonds within cellular structures. It damages the phosphodiester backbone of DNA strands, creating double-strand breaks that the cellular repair machinery struggles to address continuously. The accumulation of unrepaired or misrepaired DNA damage over time manifests as elevated mutation rates, increased probability of carcinogenesis, and degradation of cellular function in radiation-sensitive tissues, including the bone marrow, the gastrointestinal lining, and the central nervous system. Every day that a biological crew spends on the Martian surface fighting the thermodynamic and geometric barriers to propellant synthesis, every day that the equipment operates in the dust and cold, every day that the return window shifts with the orbital mechanics of two planets moving along elliptical paths, is a day in which subatomic particles are writing a cumulative debt into the molecular architecture of living bodies. The mathematics of radiation biology do not pause during equipment failures. They do not wait for propellant synthesis to catch up. The orbital geometry compounds the problem with brutal efficiency. Mars and Earth do not orbit the Sun at the same rate. Earth completes one orbit in approximately 365 days. Mars completes one orbit in approximately 687 days. The alignment of the two planets into a geometry favorable for transit, called a launch window, occurs only once every approximately 26 months. Miss the return window because the propellant synthesis is incomplete or because equipment has failed, and the biological crew must wait another 26 months on the irradiated frozen surface while their radiation debt continues accumulating and their food stores continue depleting. This is not an engineering inconvenience that can be solved by a better project management timeline. It is an intersection of thermodynamic, geometric, and biological physical constraints operating simultaneously, each one compounding the severity of the others. The geometric trap of the Martian gravity well demands propellant synthesized under thermodynamically unfavorable conditions on a radiation-bathed surface by biological passengers whose physical resilience is being continuously eroded by the same environment that makes propellant synthesis difficult. The popular conception of interplanetary travel as a symmetrical round trip is built on an implicit analogy to terrestrial transportation that the physics simply does not support. When you drive a car to a destination and return home, both halves of the journey draw on the same energy infrastructure, the same fuel distribution network, the same road surface, the same atmospheric conditions, the same gravitational environment. The physical conditions of the outbound trip are the physical conditions of the return trip. Symmetry holds because the environment is uniform. The cosmos does not offer uniform environments. The cosmos is composed of geometric depressions of different depths, surrounded by different thermodynamic resources, with different radiation exposures under different atmospheric pressures, at different solar irradiance levels, with different orbital mechanics governing when transits are even physically possible. Every destination in the solar system is physically distinct from every other destination in ways that break the intuitive symmetry of round-trip travel at its foundation. What Mars presents is not primarily a rocket engineering problem. Rocket engineering is the discipline of managing chemical energy release and directed thrust within the constraints that the underlying physics imposes. The underlying physics in the case of a crewed Mars return mission is a cascading sequence of thermodynamic, geometric, and biological barriers, each one individually formidable, collectively representing a physical challenge of a different order from anything human civilization has previously attempted. The arrow of time runs in one direction. The second law of thermodynamics is not a guideline. The gravitational geometry of space-time imposes real energetic costs on departures from planetary surfaces. The absence of a Martian magnetic field is a fixed feature of the planet's geophysical history, not a parameter available for engineering adjustment. These are not obstacles placed in the path of human ingenuity waiting to be removed. They are features of physical reality that define the terms on which any biological organism can survive and operate in that environment. To return from Mars requires not merely more powerful rockets, it requires winning a sustained thermodynamic argument with a universe that is not inclined to cooperate. It requires synthesizing concentrated order in an environment defined by dispersal and disorder. It requires climbing out of a space-time depression using energy that the destination world does not naturally possess. It requires doing all of this while time flows forward and radiation continues its work on biological tissue. The magnificence of human curiosity drives us to imagine standing on that red frozen surface and looking up at the pale distant disk of Earth hanging in a salmon-colored sky. That image is not impossible, but the ink, once dispersed through the water, does not return to the dropper on its own. The geometry of space-time does not curve upward simply because we would prefer it to. The second law does not grant exceptions to well-intentioned explorers. The reason you cannot easily return from Mars is not that the rockets are not powerful enough. The reason is that the cosmos itself is not symmetric, that time has a direction, that entropy has a preference, and that the physical price of reversing a planetary scale